My camera just turned off, which tells me that I didn't film anything. So I'm going to start again. So, in A-level further maths, there's these two things that are introduced called the hyperbolic functions. This is what they look like. There you go. Cosh x, hyperbolic cosine, is e to the x plus e to the minus x over 2. Sin x is e to the x minus e to the minus x over 2. In A-level, you're not told where these have come from. There is no derivation. And I find that kind of thing really frustrating, that you're given these kind of things and you're meant to just believe where they came from. But the thing is that you can actually prove where they come from using A-level knowledge, the Maclaurin series and complex numbers. And I'm going to do it all in this one video. It's a little bit ambitious, but I just want to do it now and put it to bed. Right. Okay, what we're going to do then is we're going to first look at what's called a power series. I believe that it's also called a Maclaurin series, named after the mathematician who found it, but we're just going to call it a power series because the fact that the power changes is the most important thing. What we want to do, right, is we want to look at something like sine of x. And we're going to say, I wonder if we could write this as an infinite series in increasing powers of x. So you're going to have like some constant plus a coefficient times x plus another coefficient times by x squared plus and so on and so on. I'm going to have to scratch my ear. So we want to see if there's a form where we can equivalently write sine of x as this infinite series. All we need to do is figure out what these a, b, c, all these coefficients are. So we're going to start off, we're going to go, right, let's get this first one, a, right. Well, a is the only term without an x, so we're going to say, right, well, sin of 0 is a plus all them, but they're all going to be 0 because it's b times 0 or c times 0. So we just find that sin of 0 is a, and sin of 0 is, you put it into calculus, well, it's just 0, isn't it? So we figured out that is 0. Now we need to get the next one. Now there's nothing we can substitute in for x here, because if we substitute in anything, right, 1, that's going to be b times 1, 1, c times 1. So sin of 1 would be b plus c plus d plus e plus all the others. Now remember, this doesn't just stop at z. It's an infinite series, it's going to go on, it's going to use every other symbol and an infinite number of symbols for the coefficients. So what do we do? To get this one, what we're going to do, differentiate both sides. So if we differentiate both sides, we're going to do the derivative of sine x. The derivative of sine x, if you've not done it yet, is just cosine of x. And then we're going to differentiate each one of these. So if you differentiate 0, the constant term, 0. Go on to the next one, if we differentiate that one, I'm not happy about how I'm laying out this board. Let's just remove all these. Differentiate bx, b, differentiate cx squared. So what I've done is I've just gone through and differentiated each bit. So that now means we've got, let's do that, cos x equals all of this. So this step, going from there to there, we just differentiated everything. Now we're going to play our little game again. because we've just got b by itself. There's no x on there. So we're going to do, all right, okay, cos of 0 is 0 plus 0 plus, oh, no, b plus 2 times c times 0, 0 plus 0 plus so on and so on. So we find b is equal to cos of 0. Cos of 0 is 1. So okay, we've got this term here. It's just b is 1. We've got that. Now we're going to do the same thing again. We're going to dy by dx again. So we're going to dy by dx, differentiate cos of x, and we're going to get minus sine of x. That's just another definition of derivatives of trig functions. And now we've got, all right, that's a 0, differentiate that, 0, differentiate this. We're going to get 2c plus 6 dx, power to the front, minus 1 off the power, plus 12ax plus so on and so on. Okay, so we do the same again. We're going to say let x equal 0 and just do a load of magic. So minus sine of 0 is equal to 2c then. That's what we've got, because those are the only bits which are not 0. But funnily enough, sine of 0 is 0, so that means that is 0, so c is 0. So this, that goes to 0. So this term, 0. What we eventually get, if we go through all the motions, is we keep doing this for over and over again, and this is the series that you get. We get sin x equals x, so I've skipped out this one because that, is 0. X, then the next one would have been minus x cubed over, it was actually 6, I think we saw that. I've written it as 3 factorial. Next one was 0, then the one after that is x to the 5 over, turns out it's just 5 factorial, because you're moving that power down all the time. So it's going to be 5 at the front, then it's going to be 4, then it's going to be 3, 2, until it's finally the 1. We just keep going, and this is it. This is the sine power series. Power series. Similarly, there's a cosine one, and I need to remind myself what that is. Sine, cosine. Notice how this has got all the odd terms. This has got all the even terms. Quite important that to notice. And it always flips between minus, plus, minus, plus. So it starts on a plus, then it's minus, and goes on forever. I've written a plus at the end here, but really it's minus the next term because of where I wrote it. So, now these, just to really hammer it home, the Maclaurin series, the power series, is if you write a function, f of x, then the power series version of it is in A-level further maths, I'm pretty sure this is in a formula book. So you've got this function, you want to express it as an infinite power series. So the first term is just the function at 0. The next term is the derivative of the function at 0 times by x. The next one is the second derivative of the function at 0 divided by 2 factorial times by x squared. Third one, well, not the third one really. The next one is the third derivative at 0 divided by 3 factorial times by x to the power of 3. Now it's not bad to remember because everywhere it's the first second derivative divided by 2 and x to the power of 2, and you just go on for like that. It's always a plus in between. Anyway, that's the power series. This is all just part of our journey, because the next thing that we're going to do is look at the exponential version of this. Okay, this is the exponential power series. Now this is quite a nice one, and where this comes from is from, who was it? Euler. Was looking at things to do with like taxes or interest and that kind of stuff. But this is the power series anyway that came out of it. Infinite series, add in every single term. Okay. What you'll notice though is, look, we've got parts of this. I've missed a term. Oh man. Missed the X one. Right. We've got parts of each of sine and cosine. Look, we've got this one. We've got this. We've got this. On that. But then also we've got this. And so on. So there's some kind of link between the two, but it's not like a perfect link. We can't just say, okay, this is this and that is that. Because now we have to start thinking about complex numbers. If I look back at here, let's remove all these bits. I'm going to swap this e to the x. I'm going to swap it for I theta. Theta is just our variable, but there's an I in there as well. So what happens is that each of these terms, this is going to become, let's rewrite it. Now this bit, we're going to do I theta all squared. I squared is going to be minus 1. So actually it's going to be minus, there we go. All right, cool. And then we're going to go on to the next one, plus, so it's going to be I cubed, which is going to be minus 1 times I, so it's going to be minus I theta cubed. Okay, there we go. Is this showing up on there? Yeah. This camera's gone and cut out, I reckon. Okay, so I'm just putting all these in there, and what we'll get at the end of it is quite nice. So if we go on to this next one, it's to the power of 4. I to the power of 4 is going to be just plus 1, so that becomes, and so on and so on. The end product, what we get there, notice how it was like the other one. Let's just put that back as it was. So like this one, but now we've got these like minus signs randomly dotted in. And the good thing about that is that what we can say is, all right, now let's look at this. This is 1 minus this squared bit plus the 4. Well, cosine was 1, then minus, then plus, then minus. All that bit's just cosine of theta. So we can do all that and just say that's cosine of theta. But then we look at these ones, I theta minus the cubed bit. Whoa, we had a minus the cubed bit here. Then the next one would be a plus, and that's a plus there. So what we'll realise if we paired all this up is it's just cosine of theta plus, well, it is the sine one, but it's I times by every term in the sine one. So it's going to be I sine theta. This is quite important, right? Because what this is we're suddenly realising that this infinite series can be written like that. Just by comparing them, this complex function can be written like that. Now that's the main part. So let's recap what we did. Power series for sine, cosine, then e to the x. Then what we did was we made this e to the x power series into a complex power series. I realised that that is just a combination of the cosine power series and I times the sine power series. And we've got this end product. So I'm going to have to erase some stuff, make some room. Okay, so this is where we're up to. This is a way of expressing a complex number now. So if you recall your complex numbers, there's ways you can express them using x and y, right? We could have the real part, the imaginary part. Then you can also do it in terms of the argument and modulus. So like saying it's an angle, which is the argument, and then a modulus, some distance to the complex number. But now we've got this new way, which is exponential model, well, exponential version. Yeah. If you wanted to have this having some argument r, you would just put an r in front of it, because then it would be. These come up in engineering and physics an awful lot. But the thing that we're doing now is looking at this, and all we're going to do is go, right, well, because of how this works, if we were to put in a minus number into that previous exponential model, we could then figure out that this was true. All right, the camera cut out and it's so chalky in here. These are our two little situations we've got, our two equations. Now they are simultaneous equations, they're both from the power series. What we're going to do now though is we're going to add each one to each other. So on the left hand side, we get that. On the right hand side we've got two cos thetas. And then we've got an I sine theta and a minus I sine theta. Oh, so that's it. Cool. Right, now what we're going to do is we're going to move that over there, divide by 2, and look at this. It's looking like the real deal already. But there's a problem. Here we've got an I theta, and there we haven't. So we're going to do this really cheeky little substitution. We're going to do this. Is weird, this. You'll like it. Let theta equal ix. Yeah, we're going to let theta equal ix. Everywhere, we're going to replace the theta with an I and an x. So we're going to get e to the power of I squared x. I squared is minus, so it's minus x, plus e to the power of, so it's minus, so it's plus x over 2. And then on this side, we're going to get equal to cosine ix. Cosine of ix. You know what? Let's call this cosine of ix cosh of x. That's that one. But what about the sine? Okay. Well, there we added them. How about we do that one minus that one? So then we'll get we might have to fudge this last bit. But we're going to do the same again. Let theta equal ix. So we're going to swap this. This is going to become a the signs are wrong. I need to think about different white balance. Right, I finished my dib dab and I've decided. Where's my chalk? This method that we do to get cosh x doesn't work exactly well for shine x. You see, the problem is, if we do the same thing of letting theta equal ix, what we get is e to the minus x minus e to the x, which isn't the definition. So what we could do is we could hack it and say, all right, well, let's say let theta equal minus I to the ix, right? Theta equals minus ix, which means that that's going to be a plus now, and that's a minus. Okay, good, right? But now we've got that. And what do you do then? Do you then go, well, let's say that this I sine of minus ix is equal to sine of x. Not really, I don't really like that, but the end of this is that cosh of x is that, and sine of x is this. This, although it doesn't look like it says sine of x, it's just how mathematicians pronounce it. The actual reason of why, or why this is, let's just write it this way around. Why it's so significant, these look so similar but are different, is because this cosine is what's called an even function, if I've got that the right way around, where you can like flip it in the y-axis and you get the same thing. Sine is an odd function where you could rotate it 180 degrees about the origin and you get the same thing. One really nice way of writing something which isn't an odd or an even function is to write it as a combination of two other functions. So that's kind of like what's going on. That last bit didn't make sense. Anyway, that's kind of a haphazard, fudgy way of making a derivation of these. Not great, but we got there in the end, and I think that kind of puts it to bed enough to continue with the rest of hyperbolic functions for A level. Interestingly enough, if you look on the internet, there's no clear derivation of this kind of stuff. There really is not. And this kind of method that I use is ones which are used in engineering university books. So this was something that I referenced a little bit whilst going through the video, just to remind myself some of the power series and that kind of stuff. But anyway, onwards from here. All right, try and edit that down.